So you remember that last time we were interrupted in the middle of something. So we had to end the lecture in the middle of this. So let me write this down and remind you of what we were talking about. So we have the definition of a Lie algebra, where these indices go from 1 to n, if the algebra has n generators. And the Jacobi identity, if you use the Jacobi identity, you show that if you define this matrix TA, BD, whose row and entry, A labels the matrix, B and D labels the row and column, in terms of the structure constant in this way, you discover that Jacobi implies that T, these matrices represent the algebra. And this is the adjoint representation. So in the case of SU3, as we discussed, this is 8 by 8. And the dimension of the representation is equal to the number of generators. Okay. And then we define the Cartan metric. And it was at this point that we were interrupted. The Cartan metric, GAB, is simply the trace of TATB, which physicists take to be delta AB anyway. The physicists normalize their matrices. But in general, mathematicians, it may be useful not to specify, not to take GAB to be Euclidean. But we'll always assume that the inverse exists. Okay, we'll let the more mathematical of you, amongst you, to worry about what happens if the inverse doesn't exist. So the inverse is GAB. Now here's a nice exercise. So as we have seen from the examples of SU2 and SU3, that the structure constant is totally anti-symmetric, is the totally anti-symmetric symbol, okay, of Levi-Civita. And from the definition of the structure constant, it's clear that it's anti-symmetric in A and B. But is it anti-symmetric when you interchange B and C? But you can, this is not a well-defined question since B and C are different animals, right? One is upstairs, the other is downstairs. You cannot really interchange them. So what you have to do is to raise the index C upstairs and define this as FABD. So the exercise is to prove that this is anti-symmetric, totally anti-symmetric. Okay, so this is a nice exercise. Incidentally, this is a source of confusion among some students because sometimes people think that this object is anti-symmetric in B and C, but as we'll see shortly, it's not. Okay, good. So any questions? Okay. Yeah.
If I have worked out the generators of the algebra under the defining
Representation, yes.
then how can I define the Cartan metric with those generators?
Well, the Cartan metric, by definition, just is defined in terms of the structure constant. Now, of course, if you know the representation, defining representation, you also know the structure constant, right? But just by computing the matrices in the defining representation. Then you just perform the sum. Notice the sum is just sum over these two indices. Okay?
If I take the trace of, if I have the generators in the defining representation, and I take the trace of...
No, you don't take the trace. You take the matrices of the defining generation. You use this formula directly. The matrices of defining representation will give you the structure constants, and then you use the structure constant to calculate the metric. Okay. Okay. So now, I'm sorry I have to go a little bit faster because we're running a little bit out of time. Out of the n xa's, as before, we find the maximal subset of mutually commuting generators, HI, and there are L of these, and L is called the rank, as I said last time. So HI, is equal to 0. Okay, so by famous theorem of linear algebra, the HIs could be simultaneously diagonalized if you think of them as matrices. And the other n by minus L generators, at this stage will be a little bit vague. We'll call them E's, okay, to follow Catan's notation. So again, let's relate this to something you know. For SU3, the H's are, of course, lambda 3 and lambda 8. They are the isospin and hypercharge, if you go back in the history of physics. And the E's are the I, U, V. As I said, the American song, I scream, you scream, we all scream for ice cream. I, U, V spin. Okay. Now, a trivial lemma is that we can choose the E's. So in basis where the H's are diagonal. So as I said, since they commute, it could be simultaneously diagonalized. So we can choose the E's to have 0 diagonal elements, along the diagonals. This is just a trivial lemma, because if the E's have diagonal elements, you can always subtract them off, because those diagonal elements would be linear combination of the H's and of the identity, right? Okay. So now we, in the adjoint representation, this statement is, of course, Ti, Tj, 0. So the T's could be diagonalized. So strictly speaking, in this mathematical notation, the H's you think of as as some abstract object, and T as the representation of those objects. So if we think of H's as the defining representation, they're 3 by 3 matrices, and the T's are 8 by 8 matrices. Okay. Now, the T's are diagonal, so we can write them. We can write give some names to the diagonal elements. So we just write Ti AB, okay, is equal to minus. So these minus signs are just to make some of the formulas look nice, to beta I n. So remember, this is an n by n matrix. So there's 1, 2, 3, 4 down to n, and of course 0. And this is the AB element. Okay, so you should pay attention here, because the indices are also different kind of animals. The I goes from 1 to L, right? But A and B goes from 1 to N. Okay. So we can also write this as minus beta IA delta AB. And this just says that the matrix is diagonal, and each diagonal element is beta IA. Now notice that I carefully, and this is how some textbooks are distinguished, I very carefully not write the A as an index, because to emphasize that it's not summed. A is not summed. Okay, beta IA is just a bunch of numbers that depends on A. Okay, but A is not an index. I find that students get very confused in some books when it's written as a beta IA as an index. Then people think that A is summed. Obviously, it's not summed. But this is a very ugly notation. This is one of the ugliest notation I've ever seen. It's kind of, this. Well, anyway, it's a very awkward-looking thing, but that's what it is. Now, one trivial remark is hermiticity. Hermiticity implies that beta IA are real. This is a Hermitian matrix. Okay. Now, last time during the intermission, or maybe last time after the lecture, one of the students asked me a question. I won't identify the student, but I realized he was a little bit confused because he said for SO3, the three generators are antisymmetric matrix. How can you diagonalize them? Well, you can diagonalize one of them. You cannot diagonalize all of them. But if you diagonalize one of them, the other two are no longer in the original basis. So you have to be careful in this discussion, okay, which basis you're in. And some students here are very confused because so what we're basically doing is going away from the Cartesian basis to a circular basis. It's when you study electromagnetism, there's longitudinal and transverse polarization, but you go to a basis in which there's circular polarization. So the E's are going to be in the circular polarization, if that helps you to understand what's going on. This answers the student's question. Yeah?
You said Hermitian in what indices?
These matrices, Ti, Tj's are Hermitian, because we're only studying algebras in which the generators are Hermitian. Okay. Other questions, please? Okay. So we have a very strange looking relationship, which is one of these very ugly relationships that looks like the indices don't match, okay? Because here so we're going to compare two equations. This one and this one. If we compare these two, we see that this thing is it's really too low tech in this digital age. Okay. Okay. Maybe, I don't know, French have bigger ears, maybe. I don't know. So we see that this, we compare these two expressions, and we see we have this rather strange and ugly looking expression, IAB, right, is equal to beta IA delta AB. We'll use this relationship shortly, but it bothers me to even write things like this. Okay. Okay. Now, remember, everything is now going to be in the basis, I won't write this again, in which the HI's are diagonal. So now let's consider HI commuted with XA, where XA would be the other guys. That is to say, the thing in the algebra which is not the H, not the H's. We already know the H's commute with each other. So commute H with the other X's. So the X's are like in the SO3 algebra, in the rotation algebra, if HI is just J3, the J around the Z direction, these other guys are them J plus and J minus, okay, the raising and lowering operator. Okay, so we can write this as IF IAB XB. That's from the definition of the Lie algebra, right? But here we plug in this expression that we know that this is beta IA delta AB XB. But B is summed over, so this just makes, this sets B equal to A because of the Kronecker delta. So this is beta IA XA. Okay? So we learned something remarkable, but this is already something you know from the rotation algebra, that when you commute HI with one of these other guys, XA, not H themselves, the answer is just that because A is not summed over, again, I emphasize A not summed over, NS, not summed. This says that you just multiply A, whenever you commute with XA, you just multiply by beta IA. So it's very simple, the action. So this is, you know, from the rotation algebra and from our discussion of SU2 and SU3, that when you commute J3, for example, the rotation around the third axis with J plus or minus, you just multiply J plus or minus by plus or minus. Okay, I see people nodding their heads. So, okay. So from this, we can write down the roots. And in fact, from this, we see, from this discussion, we see we can write down the root vectors immediately using the same strategy as before. Using same strategy. Okay, as before. Okay, so the diagonal elements, you remember that what I did is I wrote down the representation in the, well, anyway, I wrote down each of these matrices, some diagonal, and so on. And it's beta 1A, beta 1, 1, beta 1, 2, the diagonal elements, beta 1, 3, beta 1, n, right? And this is beta 2, 1, beta 2, 2, and so on. And this is beta 3, 1, and all the way down to TL, the L of them. Beta L, 1, and so on. Well, but now we can just, this is exactly what I did last week or the week before. The only difference is that we were doing using the defining representation, and here we're going to be using the adjoint representation. Okay, so the root vectors are just these. We just read off the columns, right? Now remember that when we did the when we used the defining representation for SU3, these things were the three quarks, if you like. So what we read off were the weight vectors, and we have to subtract them to get the roots. But here we're doing the adjoint, so we're doing the adjoint representation. So you can see that if I just, these vectors are already the root vectors because they just connect the origin in all possible ways. Okay? So there are n of them. So this is kind of a funny kind of inversion, you know, the indices, so to speak, change place. So the root vectors are beta, root vector A is the column vector B1 of A, B2 of A. That's the eighth root vector. So for each A, one root vector. Now we go to a better notation. First of all, trivial improvement in notation, just drop the arrow. So we don't have to write the arrow all the time. We'll be dropping the arrow. So the better notation is better notation for these XAs, these X's that are not H's. We're going to call them E. We're going to identify by their root vector, okay? And since we're going to drop the arrow, we're just going to write them as EB, E beta, okay? So the generators are then named the generators not in the Cartan subalgebra, are named for the jobs they do. Okay? So this is just like in SU3, you name them. It's silly to be like Gell-Mann and have to invent some names and to use some children's song about ice cream and so on to give names to the generators. You just identify the generators by the root vectors. So, you know, I is this root vector, and U is this one, and V is that one. So this is exactly the same as in Europe, right? When people are named for the jobs they do, like Baker, Smith, Cooper, and so on. And in France, Boulanger, and so on and so forth. Okay? So we're also going to name the generators for the job they do. That seems like a good thing. Okay? So yesterday I had to meet Michel Leduc, and I asked Henri Hollande if that means her ancestor must be a duke. So he said quite possibly, but you never know. So this is how we name generators. So if we name generators this way, then we can write this equation, this result that we have, rewrite in this very nice way, which is HI E beta is beta I E beta. Okay? So notice the I index goes here, is the root vector, and now this clumsy notation, this little a, disappears because people identify by their root vectors. Okay? Now, trivial exercise. Let's see. Okay, I hope people can still see this. Trivial exercise is Mr. Hermite told us to Hermitian conjugate this. If you Hermitian conjugate this guy, you get HI E beta dagger. But when you Hermitian conjugate a product of two matrices, of course you reverse the order so the commutator gets a minus sign. And then this is the beta we already said is real, right? So this is E beta dagger. So if we move this minus sign to this and write it as minus beta here, we see that E beta dagger is E minus beta. Okay, so the theorem, if you call it a theorem, is that for every root, if the root given a root beta, and here I put the vector back as to emphasize this, then minus beta also a root. Okay, so this is just that for every root vector, there's the opposite is also a root vector. So in the case of SU2, this is just this theorem, just the statement that when you if you can climb up the ladder, you can also climb down the ladder. Okay. Now, but just from this, we have immediately an interesting theorem. So remember that L is the rank of the algebra, and N is the number of generators. Okay? So immediately n minus L we know must be an even integer. Because the number of root vectors is n minus n. N is the total number of generators, and if you take away the ones in the Cartan subalgebra, it has to be even number of them, because if beta is a root, minus beta is a root. Okay. Now, the thing that we discovered earlier when we were talking about the orthogonal groups are not so surprising anymore. So the theorem that follows is if the number of generators is odd, the rank must be odd. If the number of generators is even, then the rank must be even. So there's this rule. Is that clear? Right? So now we can apply this to the example that we discovered 2 weeks ago, 3 weeks ago. So I guess I could erase any of this. I hope this is not going too fast for the students. If you're seeing this for the first time, then you really should read the book or work out all the exercises and so on. So last time we discovered the following, we discovered the following interesting thing, that SO4 is a rank 2 algebra, and SO5 is obviously a larger algebra than SO4, obviously contains SO4 as a subalgebra. It's also rank 2. So unlike human society, the bigger guy does not necessarily rank higher. Although it contains the other guy, it's still the same rank. Okay, so SO4 is 4 times 4 minus 1 over 2 generators, which is 6 generators. And SO5 is 5 times 5 minus 1 over 2, and which is 10 generators. So they both have even number of generators, even though this is bigger than that guy. But this shows the rank cannot go up in this case. But you see, if you look at SO6, then it's different. 6 times 6 minus 1 over 2 is what? 5 times 6 is 15. So it has odd number of generators. So its rank must be odd. It cannot have rank 2. So that, in fact, is rank 3. So this is a little, very small theorem like this already gave us an interesting result. Okay. So let me now raise this up. Now, so we have now the commutator between H and H is 0. Between H and E is given by something. So what about the commutator of E alpha with E beta? What is this equal to if we commute two things? Commute these two E's. To see what it does, the question is to ask, what does HI do to this object, right? So I don't know what we would do if we did not have Jacobi in this subject, because that's the only tool you have almost. So we ask Jacobi again, and Mr. Jacobi say that this is equal to E alpha, E beta, HI, minus E beta, HI, E alpha. But this guy is minus beta I, E beta. There's a minus sign, right? Because H and E are in the opposite order, and here H and E is in the same order. It's alpha I, E alpha. So this is E alpha, E beta. This is E beta, E alpha, but with an extra minus sign. But then it comes together. You see that this is alpha I plus beta I, E alpha, E beta. Therefore, E alpha, E beta has the root alpha plus beta. But this we saw in SU3 already. SU3, so SU3, as I said, is very important, and I spent a lot of time on SU3. Not necessarily because of its intrinsic importance to particle physics, but SU3 is important because it's really the prototype of a Lie algebra. Almost everything that happens in the algebra happens in SU3, except for things like the roots all have equal length and things like this, which is not true in general. Yeah. Okay? So therefore, E alpha, E beta, the commutator E alpha, E beta is proportional to E alpha plus beta. So just add the root vectors. Root vectors add. So what we've shown here is just the root vectors add. Now, of course, I went over there, and so some people are obviously worried about this. There's no reason this is equal to this. In general, there could be a coefficient. And this coefficient could depend on alpha and beta, of course. And this also covers the possibility in which E alpha, E beta commutes, because then n would just be 0. Could be 0. So in SU3, we saw an example of this. If you add the root vector, this one, to this one, we get the root vector, this thing. But this root vector doesn't exist, the vertical one. So those two generators must commute. Okay, so one very nice feature of adding root vectors is that without commuting matrices, you know that some of the commutators are 0 immediately. Okay? Now, again, for students, exercise, these are that n's have various properties that you can prove. For example, n alpha beta is minus n star minus beta minus alpha. Well, that's just a trivial exercise because you obviously Hermitian conjugate this to get the complex conjugate. So things like this. You should do all the exercises in the book if you really want to understand what's going on. Okay, so we press on. Okay, so here we see the commutator of E alpha, E beta is N alpha beta E alpha beta plus beta. Now, then here comes the interesting question is what about E alpha, what is E alpha, E minus alpha? Go to what? What if alpha plus beta is equal to 0? Okay, so what is E alpha, E minus alpha? So again, we ask the same questions. What does HI do to this thing? And again, I let you do an exercise. If you go through the step, well, it's trivial. In fact, the exercise is already done in this line. Of course, you get if alpha plus beta is 0, then this HI commuted with this thing is 0. But the Cartan subalgebra was supposed to be maximal. You have found the maximum number of things that commute with each other. So it follows that this thing must be a linear combination of the H square. Okay. Okay, so therefore it's HI times some coefficient. Okay. Now this coefficient, so E alpha, E minus alpha is equal to linear combination to HI's. So there's a bunch of coefficients here that I have to write down. But now I'm going to use a very sneaky notation. I'm going to write the coefficient as alpha I, alpha sub I. Okay. Now this is this. Where did alpha I first appear? Okay. So, but there was an alpha upper I with the upper index, and this is an alpha I with a low index. So we have obtained we define the root vector as beta I e beta. So this has an upper index all along, but this has a lower index. So this is summed over I. So the notation we are anticipating, at this point we don't know whether alpha I is related to alpha upper I, which is the root vector. But of course, I already gave away the surprise by this notation. We're going to show that alpha sub I and alpha upper I are related. Okay? Now how do we prove this? To prove this is we're going to multiply by Hj and trace. Okay, and I'll do it for you. The right hand side becomes alpha I trace Hi Hj, and the left hand side becomes E alpha E minus alpha Hj, and we now have two terms, trace E alpha E minus alpha Hj minus trace E minus alpha E alpha Hj. So now we use the fact that the trace is cyclic. Use the property that it's cyclic, and we get that this is trace of e to the minus alpha Hj E alpha. Okay. But Hj E alpha, see, it's all very beautiful, this Cartan's discovery. Hj alpha, this is Hj with E alpha is alpha j E alpha. And so this is alpha j trace of E alpha dagger E alpha. Okay? So that's the left hand side. So pause for a second. Everybody, all the students are following this. Okay? When you just calculate the right hand side, and you find that it's equal to this. Okay. Now what about the right hand side? The right hand side is, you're going to see in a second what it is. In the Cartan basis, I have not erased this. It's nice here. GAB. That's the metric. Trace Hi Hj is part of the metric. In fact, you see that trace Hi Hj is them Gij in this basis. So, but we also remember I have a remark that I could choose the trace of Hi's and the E's, the H and the E's to be 0. By definition, I can, this is like, it would be silly, for example, in the case of SU3, you chose the lambda 3 and lambda 8 to be diagonal, but then the I's and V's and U's, if you add some diagonal elements, that's clearly silly. You can always subtract them off. So this means that you can always choose the basis GAB to be diagonal, that the off-diagonal elements are 0. That's what this means. And then there's some stuff down there that you don't care about. Okay? So if you do this, then this is in fact Gij. So this is alpha I Gij. the metric. Okay, so now we obtain this nice result. But then you still have a question, what is this? Trace of E alpha, dagger E alpha. How do we know what that is? Well, you know what that is because so far we have not normalized E alpha, right? Not normalized yet. E alpha is not yet normalized. Not yet normalized. And we're going to normalize him now. So let's grab the guy and normalize him at this point. So we just normalize him by defining this to be 1. So if you like, this is definition. Okay. So if we do this, you see that alpha I Gij is alpha j as claimed. So the notation is good. Alpha I is just alpha j with the indices lowered. And of course, now we can multiply by the inverse of Gij and show that alpha I and alpha j are related. So in fact, as I said, mathematicians sometimes don't choose the same basis as physicists. Any reasonable physicist, for example, would choose the space to be Euclidean. But Chevalier, for example, in the Chevalier basis, as I said, did not choose the basis to be Euclidean. Now, then this metric, the existence of a metric is clearly important because given root vectors, we can now define the scalar product between two root vectors. Alpha dot beta, mathematicians write this as alpha beta, is then Gij alpha I beta j, which is the same as Gij alpha I beta j. And again, I would omit the arrows. Okay. So that was the whole point when we looked at SU3. When we studied SU3, we found that all the root vectors have the same length, and the angle between them, they're all 60 degrees. And I asked the student whether this is always true, and so on and so forth, and to develop some intuition. So it turns out our intuition of the first one was not true. That for SO5, we discovered some root vectors are longer than the other root vectors. So there was a long root and a short root. But for SU3 was true. So then there was also the question whether the angles between the root vectors are always nice, like 60 degrees or 45 degrees or so on. And we'll see whether that theorem is true. So this is sort of the intuition, if you like, why the Cartan classification is possible. If you're a poor man in the 19th century, try a few examples and you see the root vectors always have nice geometric properties. Okay? So then you can try to do what Cartan did. Okay, so now first I see it's almost 11. So that we have 15 minutes. So we are actually moving along. So first I would like to make a summary. We've written the Lie algebra in the Cartan basis. So this is the key to write it in a nice basis. Hij is equal to 0. Hi, so this is summary. E alpha, alpha I, E alpha, and E alpha, E beta is N alpha beta, E alpha plus beta, and then E alpha, E minus alpha is alpha I, Hi. And these two alphas are related, okay? So these alphas are related. And this is the starting point for all the theorems to come. So from this, you can classify all the Lie algebras. And this is what we will do. But before we break for intermission, let me give the student an exercise which they can do in 10 minutes while we have an intermission. Catan classified all the algebras, right? But since you're not Catan, that's what Brezan said to me yesterday. In fact, he said, I'm no Catan. This is the famous, I'm no Feynman, and so on. People say these remarks. So, since you're not Catan, you can classify all the rank 2 algebras, rank 2 Lie algebras. Okay? So for intermission, this is a nice exercise to do. Now I have not, this exercise is unfair because I actually have not given you all the tools. I haven't shown you all the theorems yet. So I actually have to prove some more theorems before I can ask you to do this. But I will write you the answer, write down the answer. The answer is so nice that it's almost hard to resist not to writing it down. So the answer is given in my book, as you can see, which Professor Guida has so nicely Xeroxed for you. Okay, so all the rank 2 algebras. There's this guy. This is what physicists call SO4 and what mathematicians call D2. There's this guy. Which is what physicists call SU3 and what mathematicians call A2. Okay. So the hexagon, the squares, and then there is this one. Which is what physicists call SO5 and what mathematicians call B2. And then there is this one. So this is the example that showed that roots can be different lengths. Then there's this one, which was we discussed last time, was the symplectic group, SP4, which mathematicians call C2. Okay? So the surprise is that this and this is just rotated by 45 degrees. So these algebras are isomorphic. SP4 and SO5 are isomorphic, which is not exactly trivial to see if you think about the definition of SP4 and SO5. Okay? And also notice that mathematicians, SO4 and SO5 are not even in the same family. SO4 is in the D family, and SO5 is in the B family. So actually, mathematicians find physicists very strange. You could put all the SO groups in SO algebras in the same, even at same names. But now comes the big surprise. If you could do this exercise before during intermission, here's the big surprise: that there is one more algebra which does not fit into what physicists know, and I'll try to draw it as well as I can. Okay, surprise. A new one. And this even has some relevance to Christmas or something, to this time of year. So as you know, it's the Star of David. So it's the algebra mathematicians call G2, and mathematicians call these the exceptional, one of the exceptional algebras. And physicists sometimes call the Star of David algebra. And so remember the story I told you? There were these physicists who know a lot about the algebras, and they were misled by experiment. While Gell-Mann proposed SU3, these people proposed G2. And so while Gell-Mann got the Nobel Prize, nobody even remembers these guys. Okay, oh, I remember some of these guys. So this is the big surprise that you get from the Cartan classification. And again, you see that the roots are different lengths. And so how the geometrical patterns come in is really extremely interesting. Okay, so this is a good time for a break. Yeah?
Does it have another name? Because Star of David I never heard of.
No, physically, yeah, called, that was just a joke. This is called G2.
Nothing like E or
No, there's no E16. The biggest is E8. Okay, but those are higher ranked. But rank 2, that's it. Yeah. Your question?
Yes. Later after this proposal of G2, was there anyone still working on that with particles beyond the standard model?
No, many people believe in, well, as you know, the exceptional algebras may really come into physics. And in fact, the really surprising thing is that last year, well, first of all, in particle physics, people that work on grand unified theories, E6 is a very strong possibility. So E6, in fact, if you use mathematician notation, as you know, in grand unified theories are based on SU5 and SO10. And if you look at the Dynkin diagrams, there's exceptional algebra E6, and SO10 is a subgroup of subalgebra of E6. And the thing that is really sort of intriguing, which suggests that physicists might be on the right path, is that mathematicians in the same series could also identify SO10 as E5 and SU5 as E4. Then the other clue is, of course, as you probably know, that string theory favors E8. So E8 comes in string theory. But the really amazing thing, which I find absolutely amazing, is condensed matter physics. So last year we had a seminar in condensed matter physics in Santa Barbara, and the guy announced, and he's an experimentalist, he's discovered E8 in some system. And so so this shows that before, condensed well, anyway, so it's pretty surprising. E8 has appeared now in condensed matter physics also. Well, there is Mr. Google. You ask Mr. Google. Why ask me? Okay. All right, so we have an intermission. You can see the Cartan reduced the problem of classifying all the algebra to these equations. So we ask ourselves, what could we do with this? And again, we take some inspiration. We'll take inspiration from SU2 and SU3. So we know from the angular momentum algebra, when you take a course on quantum mechanics, that when you go up the ladder must terminate at some point, because we're talking about finite algebras. And this allows us to say something about n alpha beta. Oh, okay, so if you look at this list, you see the we don't know anything about n alpha beta at this point. So what can we say about n alpha beta is the next question. So the key, what about n alpha beta? And the key is that the algebra is finite. So there are a finite number of roots. Okay. So if we keep on commuting, we have to get 0 eventually. So imagine the strategy would be to commute E alpha with E beta. So that gives us E alpha plus beta. Now we commute with E alpha again. Then we get E 2 alpha plus beta. And we keep going. We keep commuting with E alphas. And so eventually, this would be E to P alpha plus beta. But then at some point, you have to get 0, right? Because it's a finite algebra. So let P be the maximum value. So it's useful to draw a picture to understand what's going on. So let beta be this vector, this root vector. And so beta plus alpha would be going off at some angle. I don't mean to draw it as 90 degrees. So this would be beta plus alpha. And then we have beta plus 2 alpha, and so on. And so let's say it ends at beta plus 3 alpha. So in this picture, and then it ends. Okay, so in this picture, P would be equal to 3. And obviously, we can do the same thing with e to the minus alpha E beta. And we can keep on commuting, and so on. So we're going in the other direction. This would be beta minus alpha, beta minus 2 alpha, and then it ends. Okay? And so we'll say that here, the last one is minus Q alpha plus beta. So this defines two integers, P and Q. Okay? And I will call this, and now I'm going to create problems for Guida, because I want to take my sweater off. I'll call this, just invent a name, it's a chain of roots, and it's called the beta chain in the alpha direction. Right? It's pointing in the alpha direction, and it has P plus Q plus 1 roots. Contains P plus Q plus 1 roots. Okay. Now what can we do? So there's only one person who can help us, which is Jacobi again. So there's nothing else. Okay? It's only Jacobi. And so I hate to erase the nice pictures, but at some point I guess I need the space. So I will erase this, unfortunately. Okay. So Jacobi, again, Jacobi tells us if I take ek alpha plus beta, E alpha, E minus alpha, this commutator, I'm sorry, E minus alpha, of course I mean, then plus the cyclic permutation, E alpha, E minus alpha, K alpha plus beta, plus E minus alpha, Ek alpha plus beta, E alpha, that this is equal to 0. Okay? So, well, we know what this is from here. E alpha E minus alpha is just alpha I hi, in which the I is sum over. And then this one with that one, okay, is given here. The E with the H is given here. Okay? So it is first as a minus sign, because it's in the opposite order. The commutative of H is K alpha I plus beta I. It's this vector, right? With alpha I E K alpha plus beta. Let me write it like this. It's a little bit less confusing. Minus alpha I. Because E with H, we know, is from this equation. Okay? Okay, this is an interesting combination because this is K alpha alpha using the notation I used before, the Catan used. It's the scalar product between two vectors using the metric in the algebra. Then plus alpha beta. And again, I put the vectors back to emphasize its vectors. And E K alpha plus beta. Okay. So now you see how lengths and angles, the lengths of the root vector and the angles between the root vectors are going to come in. Okay, so they're all going to pop up. Okay, I can erase this. Well, but now you see what this is and what this is. You just add when you commute two E's, right? You just add the vectors, and then you add and commute again, you add another vector. But every time you commute, you get an N and an E, and then you commute again, you get another N with a E. Okay? But this E clearly is just going to be K alpha plus beta. Because you just add these three vectors, and that minus alpha and the alpha cancel each other, and they're going to E K alpha beta. And similarly, this will be some N, E K alpha plus beta. So the N's, of course, carry labels, alpha and beta and so on. But I'm not going to write them down, so you can work them out. Okay? So we clearly get a relationship because this coefficient of ek alpha, e to the k, ek alpha plus beta is common. And so we get a relationship between this, this, and this. So at this point, it is, you define something, and this thing is going to depend on k, it depends on alpha, and it depends on beta. It depends on the two root vectors and the n's. So I'm not going to write all this out in carefully. So you can find this in the book or you can work it out. Okay? I'm not going to write all this on the blackboard. So this gives you an equation for the m's. There are two different m's is equal to this. And very luckily, perhaps lucky for Catan, you find that this is actually a recursion relation, like this. It shows the m satisfy this. So exercise for students, exercise to derive. So this is the central relation in this Catan study of the algebras. Okay? So again, if you like, we can emphasize that these are vectors. So it tells you that the m with k minus 1 is related to m of k plus these two quantities that involves the length and the angle between the root vectors. Okay. But so this is a recursion. But the nice thing is, of course, you know the starting point and the end point. because we already said that we're saying that it ends, the maximum one is a P, and the minimum, and the minimum one, it's a beta. It starts with beta plus Q alpha, and it ends with, study with beta plus P alpha, and it ends with beta minus Q alpha. So then the m that is higher than this would have to be 0. So this is enough to fix all the m's, right? Okay. So obviously, you don't expect me to work this out in real time on the blackboard. So it's for exercise for you to work this out. So exercise. So first the exercise, derive the recursion relation, and then to work out the recursion. So we find a formula for m p minus s alpha beta is equal to something another, So it's depends on it's some expression. Obviously, it depends on p, and it depends on s, and it depends on alpha, and it depends on alpha beta. Okay? So this is in the notes that Xerox give to you for you today is equation 40 on page 374. Okay, so we don't have to worry about what the equation says, but you work through this out. You see that you start with the thing at P, which is the maximal, and you keep going down, go down. So you're climbing down the ladder. You climb down S steps, and you get you determine this M completely. It depends on P, depends on S, it depends on these two lengths and angles. Okay. So now the requirement is that it has to end at beta minus Q alpha. So when you plug in S is equal to plug in S equal to P plus Q plus 1, then this thing must vanish. So the condition is that the right-hand side must be equal to 0 when you plug in S equal to P plus Q plus 1. So obviously, you get some relationship between between the lengths, angles, and P and Q. Okay? So I don't do the arithmetic for you, but the logic of the arithmetic is what's important here. So to really understand what's going on, you really have to go home, and if you're a serious student, you have to work through all this. So, Elie Cattin, whom Orlan told me this morning in the car, was a professor at Orsay. So, you know the story of Henri Cattin? No, not Elie Cattin. Henri Cattin, but not Elie Cattin. So, Elie Cattin, as I said in my book, is a triumph of the French educational system. So yesterday, because the French Inspector General found him in a small village, the son of an ironsmith, and his life was determined because he didn't have the muscles to lift the hammer. And so his father made his younger brother do the hammering. So when I told this to several people at the École Normale Supérieure, also to Henri, they all said that the French educational system has gone downhill, and it's not clear whether they could still find such people. But Eugène Crémer at the École Normale Supérieure is an example of the success of the French educational system, because he told me that when he was in school, in the French public school, he was classified as imbécile. So the fact that the French educational system could turn an imbecile into one of the world's greatest string theorists is a great success. So anyway, Elie Cattin, the father, found that a condition that the algebra must satisfy. And in the intermediate steps, you can see it's going to be quite a mess because the iteration also depends on k as you go along. So you have to use Gauss's formula to sum over k and so on. But amazingly, at the end, everything cancels. And you get this very nice condition. That's what it comes out after you work out. When you plug in this, you require the m to be 0. You obtain this. Okay. Now, for a lesser person, maybe most of the people in the room, you look at this and you say, well, what can I do? There's not much I can do. It's already stuck at this point. It seems very little information because you don't know anything about P, you don't know anything about Q. So P and Q are just two non-negative integers, non-negative integers, right? That's all you. So all you know is that this is an integer n, and this integer n can have either sign. It could be positive, it could be negative. Okay? So it looks like there's very little you can do at this point. But of course, Cattin was able to do a lot with this equation. So the first step is that if you know this, then you also know that this is some other integer. So that to me is extremely clever. That to me is probably the most clever step in this whole thing. Amazing. Okay? Because clearly nothing tells you which one is alpha, which one's beta. France is after the revolution, it's already democratic after 1789. So, except the other day I saw a sign that says Liberté, Égalité, Beyoncé. Okay, so now, again, we don't know anything about m and n except they're non-negative integers. Okay, so let's see. Okay. Well, one thing you can do, you can multiply these two, okay, which is cosine square theta alpha beta. If I multiply the two of them, I get alpha beta square, alpha alpha, beta beta. And that's equal to cosine square theta alpha beta, right? Which is equal to mn over 4. So the 2 was crucial here. It became the 4. This is obviously the cosine square of the angle between the two vectors is equal to this. Now, this is why there are only so many Lie algebras. Cattin observes that this implies mn. And since m and n are integers, there are only a finite number of possibilities. So this is really beautiful. Okay? So if you multiply these, of course, any imbecile could say at this point, you also should divide them. So you divide them, and you learn something about the lengths. So this we have seen from the example of SU3 and from some of the other algebras we work out, SO4, SO5, and so on, is that the ratio of the roots are given by integers. So it's not true if they're all equal length. All you can get out of the length is that the length square, the ratio of the length square, are given by integers. Okay, so from this, my exercise was too early in time. I gave this exercise about classifying all rank 2 algebras because I haven't told you about these 4 conditions yet. But now you have these 4 conditions. You can do the exercise. Classify all L equal to 2 algebras. Okay, so it's useful for me to write down, especially if I'm going to have to move the blackboard up. 1, 2, 3, 4. 3 and 4, of course, related 5. Okay? And I'm going to give also a name to this, which is rho alpha beta. It's the ratio of the length of the root vectors. Okay? So 3 tells us that m and n are both positive or both negative. You can see that they cannot be, one of them be positive and one be negative. 4 is the really restrictive one, okay, which is a cosine square theta beta alpha beta, which is mn over 4, could only be 0, 1/4, 1/2, 3/4, or 1. So during intermission, one student asked me, there's no technical definition of nice. So what is nice? I keep saying the angles are nice. Well, if the angles does not satisfy this, it's not nice. So in Lie algebra, these are the nice angles. Okay, remarkably, these are the only possibilities. Okay, now next we're going to use another important fact. If alpha is a root, then minus alpha is also a root. Well, this was trivial because the Hermitian conjugate of E alpha is e to the minus alpha. Okay? So that means that suppose alpha is like this and there are 2 roots, alpha and beta is like this. We can always flip alpha, change alpha to minus alpha, and call it alpha. And so this shows that the angle between alpha and beta is always acute. You can always choose it to be an acute. So I remind you, acute angle is less than or equal to 90 degrees. Right? So that's very nice. So this means that also cosine theta alpha beta then could be chosen to be positive or 0. So it's restricted to between 0 and 90 degrees. So to me, this is really one of the most beautiful chapters in mathematics. Okay. Then 1 implies n is positive, and 2 implies that m is positive or 0. And so far, which one is alpha, which one is beta, is not fixed. So we adopt a convention. We're going to call the longer guy alpha and the shorter guy beta. And if they're equal length, then we just flip a coin. It doesn't matter which one is which. So you see, by convention, therefore, by convention, m is greater than n. Okay. So there are 5 possible cases. According to that, theta alpha beta can then be 90 degrees, 60 degrees, 45 degrees, 30 degrees, and 0 degrees. And these are the ones we learned in elementary school. It's nice. Okay. Now this one, first of all, the 0 degree is not allowed. because that means alpha and beta is in the same direction. And okay, so that's not allowed. It's sort of the degenerate case. And the 90 degrees is also special. It means alpha beta is equal to 0. Okay? So that's a special case. And in fact, ever since elementary school, we learned about a red flag should have gone up when I divided to get 2. So, I'm sorry, to get 5 up there. Okay, when we obtain this. So, because when you divide these two, one of them could be 0. The red flag is that we could always have divided 0 by 0. In fact, that is the 90-degree case, because for 90 degrees, one of them, alpha commutator beta, it's not commutator, sorry. The scalar product of alpha with beta is 0. So n and m are both 0, so it's just dividing 0 by 0. So in that case, rho alpha beta, which I define as alpha alpha, the ratio of the lengths, is not determined. So that case has to be studied separately. So then there are only 3 cases, remarkably, okay, which is mn over 4 equal to 1/4, 1/2, and 3/4. Only 3 possibilities. So now we can make a table. Mn, okay, alpha alpha, beta beta, cosine square theta alpha beta, and theta alpha beta. Okay. So, since m we can by convention choose to be bigger than n, okay, the only possibility is 1, 1, 2, 1, and 3, 1, in which case the length of of these two things are 1, 2, and 3, and 1/4, 1/2, 3/4. And then this is 60 degrees, 45 degrees, and 30 degrees. Okay. So the exercise, here's another exercise, is that when we introduce the terminology long root and short root, we're implicitly assuming that there are only two lengths possible. There's no medium root, okay? So you only have long ones and short ones. And the exercise is to prove that there are only 2 lengths possible. And the proof is very simple, because this is the square root of the square of the length. So the ratio of the lengths are square root 2, square root 3. So if there's 3 of them, you cannot form, you'll be inconsistent. Okay, so there are only 2. So this is why in the Dinkin diagrams, you don't need colors, you only need black and white. Because so in the Dinkin diagram, which I hope we get to a little bit, the roots, the long roots are black circles and the short roots are white circles, vice versa, depending on your convention. Okay? So, now there are all kinds of theorems you can prove using this. So one of them is called the Weyl reflection. So I think at this point we can, well, maybe I'll keep this for a second. So there are various theorems, and the first one is, there are many, many theorems, but I'm just going to mention the important one. Given 2 roots, alpha and beta, consider beta prime, which is beta minus 2 alpha beta alpha alpha alpha, which is beta minus 2 cosine theta alpha beta the absolute value of beta times alpha. Okay, so what does this mean? This has a nice geometrical meaning. So if alpha is this vector and beta is this vector, and you form the thing that's perpendicular to alpha, it's like a mirror. You imagine a mirror and you make a mirror in reflection. This would be beta prime. Okay. So the exercise is to show that beta prime is also a root. Okay. So this is called a Weyl reflection. And again, we saw this in SU3. Once you know the two roots, you can reflect all the rest. Okay? So it's like the hall of mirrors in the Jardin d'Acclimatation. If you know two roots, you reflect. You just reflect to get this one, and then you reflect, and so on and so forth. And you can get all the roots that way. Okay? So this is called Weyl reflection, and you can prove that. Okay. Now another theorem is no more than 4 roots in a chain. So again, an exercise. So for the students, I really recommend not looking up the proof in the book, but try to prove it yourself. You cannot have more than 4 roots in a chain. Okay? So that restricts the Lie algebra enormously. Now, so therefore, good thing I kept this drawing. This one, I purposely drew it with 5 roots. 1, 2, 3, 4, 5, in fact 6. 6 roots. This is not possible. We just drew this as an intermediate step. So I did this on purpose. Okay, so once you have these theorems, you can easily find all the rank 2 algebras. Okay. Now, so finding all the algebras. So one way to put it, in what I like to say, is that physicists and mathematicians, they speak the same language but different dialects. And sometimes the dialects are very hard to understand. So here's the translation table. AL is SUL plus 1. And BL is SO2L plus 1. And CL is SP2L, and DL is SO2L. So several observations. One is that for mathematician, everything is uniformly denoted by rank. L is the rank. And physicists, for historical reasons, have these crazy things that shifted by 1, 2L plus 1, and so on. Okay? So the rank of SU3 is actually rank 2. The rank of SU3 is just 2, and so on. And the other thing is that I've already said this several times. To mathematicians, the SO groups, the odd SO groups and the even SO groups are different. Okay? They're even in different families. Then after the D's, the mathematicians then discover E6, E7, and E8. And it ends with E8 for finite Lie algebras. And then they discovered F4. And then they discovered G2. And that's it. That ends. So Catan's classification. So I probably will not have time to go over the exceptional algebras. So these are called the exceptionals. Okay? And we also talked about when we were setting up the general theory, we talk about positive and simple roots. And there are all kinds of theorems that you can prove about positive and simple roots. So another exercise for the students. Exercise. If alpha and beta are two simple roots, so you have to remember the definition of simple, two simple roots, then alpha minus beta cannot be a root. So, by the way, all these theorems are not that difficult to prove. They're all typically one or two lines in when I wrote them up. And there's so many theorems, I just picked a few when I wrote my book. I mean, if you open a mathematics book, there are many, many theorems. So by saying this, by saying that there are many, many such theorems, and all the theorems are two-line proofs, I'm trying to encourage the students to prove some theorems, to discover some new theorems. Maybe there are new theorems. So an example of this is that in SU3, for example, you discover that V plus minus U minus is not a root. So these theorems are really quite nice, right? Because without commuting the 3 by 3 matrices, you really know the commutator has to be 0. Okay. Okay. So now I can actually, I have 10 minutes left, and I could maybe only tell you one or two stories about Dinkin. No. So with the next chapter, chapter 6.5, which is also Xeroxed and given to you, Dinkin diagrams. So now we had drawn the root diagrams for rank 2 on the blackboard. Now for rank 3, it's already difficult to picture because they exist in 3-dimensional space. And then, obviously, if you have rank 29, you have to think of the root vectors in 29-dimensional space. So, very hard to imagine. And Mr. Dinkin did an amazing thing. He showed that all the root diagrams can be written on a piece of paper in 2 dimension at most. In fact, more or less almost 1 dimension if you count trees as 1 dimension. So, and his observation, in hindsight, all these things seem quite simple. In fact, it is simple because his observation is that you only care about the simple roots. Remember that we define positive roots and then simple roots. And of course, first the positive roots, the negative roots are trivial, they're just minus the positive roots. And then among the positive roots, you define the simple ones, because the non-simple ones could all be given in terms of the simple ones. So that was his brilliant observation. And again, to encourage the students, he did this when he was a student. So here's the story. The story was that he was in some class on group theory. And so once the Catan classification was explained, it seems very hard to picture the root structures. And the professor actually asked him to prepare a talk to explain the Catan classification to the other students. So while preparing his lecture, he realized that he could draw a simpler picture. Okay. So then I wrote my chapter on Dinkin diagram, which is very beautiful. And I must admit, since there's in my research, there's never been any need for using Dinkin diagrams. It's a little bit vague. And I don't know if there are any applications in condensed matter physics in which you really have to use Dinkin diagrams. Certainly in physics, as far as I know, you don't have to use Dinkin diagrams. Now, just let me tell you one amazing thing about Dinkin diagrams, perhaps you also already suspect, is that when you get to this is page 396. When you started discussing the exceptional algebras, and this is absolutely beautiful, the Platonic solids suddenly appear. And everybody here knows about Platonic solids, I assume. And this to me is absolutely astonishing, right? So, but you can already sort of see how that could happen, because it's all about vectors with same length or lengths that are square root 2 and nice angles. So things like things like cubes and icosahedrons and all kinds of things appear. Okay, so the other thing that was interesting was when I was writing this, we have a steady stream of Russian physicists coming to Santa Barbara. In fact, during intermission, I just got an email that Russian physicists have left Saclay, just left Saclay. So I got an email from Krapivsky that he's at the airport waiting for his flight. So when I was writing this, I was telling this Russian physicist how great how beautiful the Dynkin diagrams are. And he said, do you realize that Dynkin is still alive? And I was absolutely amazed. And I was really surprised by this fact, because I somehow pictured Dynkin as living with Catan and all these people, and is a historical figure. So I looked on Wikipedia, and indeed he's alive. And he was alive. So I thought I would send him an email or call him after I finished the book. But then after I finished the book, I discovered he had died in the meantime. So there was only a window of a few months. So now the other interesting thing is that if you look on Wikipedia to find out about Dynkin, is that his specialty is not group theory or algebra. His specialty was probability theory and statistics. So he was a professor of, so this was just something he did when he was a student. So it's something for you guys to think about. So when I was talking to my students, I said, well, if you cannot discover a classification, maybe you can lower your ambition and discover a diagram. So Dynkin diagrams are certainly easier to discover than Catan classification. So you can think of all the famous diagrams in physics. You could discover them. You guys are probably smart enough. Like Feynman diagrams. You can discover Feynman diagrams. You can discover Penrose diagrams, and so on. There are many diagrams to discover. Okay, so that's another interesting thing. But then the Russians also told me that Dynkin emigrated to the U.S. very early. Somehow he was able to get out. So he was actually extremely helpful to Russian physicists. When many Russian physicists first got to the U.S., they all went to see Dynkin. So that's another fact about Dynkin diagrams that I can tell you about. Okay, so too bad there's not enough time to cover Dynkin diagrams in spite of what the poster said. So we'll end the course here. Questions? Yes.
Could you please briefly comment on the graphical tools to work with infinite dimensional algebra?
Graphical tools?
Yes, like those weight, root system, root diagrams, and is there any graphical tools?
Exactly, Dynkin diagram. And now, of course, with computers, maybe you can invent some other things. I don't understand the question, but well, that's what Dynkin did. Other questions? Okay. Yeah.
These 5 exceptional algebras
Yeah.
that you said were related to Platonic solids, so it's really one-to-one, the 5 Platonic solids?
No, it's not some correspondence. It's some strange thing when you're discovering the Dynkin diagram for some for some exceptional algebra, I've forgotten which one, suddenly you get some equation, and the equations has to do with platonic solids. The solutions.
Each platonic solid has some
No. It's by the way, Dinkin diagram is very nice. By the way, you know the Dinkin diagrams also show a lot of symmetry. That so, for example, the Dinkin diagram for SO8 is like this. So it has this threefold symmetry, and this is called some mathematicians call this an inner automorphism. So some people think that SO8 is the most beautiful Lie algebra. So some particle physicists have been obsessed with SO8, thinking that SO8 must be relevant to nature somehow, which I talk about in the book a little bit. No, the platonic solids pop up in some strange way, because when you okay, so in the Dinkin diagrams, it turns out that this is a possible Dinkin diagram. This is very much close to the French educational system. The Americans would have no hope. This is, if this is P circles, and I haven't even explained to you what the circles mean. They represent the simple roots, and this is M things. Then Dinkin discovered that this must satisfy this equation. Pretty amazing, huh? And this, anybody with a French education would know it's a platonic solid, but nobody in the US would know, as far as I know. Right? The French, I certainly did not know this was a platonic solid. Yeah. Okay, so let's end the course.
Thanks again.
Yeah, I should thank the students for attending. I thought after the first lecture they would all disappear, but so it's the old people who disappeared after the first lecture.